Hello. In this paper, we're going to be looking at the proposed preparation for the Physical Sciences Return November examination. Okay. So this paper has quite a number of questions that we need to explore. And the topics for paper 1 are well known by you guys. So let's start with the mark allocation, which is 100, and the duration is basically 2 hours. And then from there, when I look at the instructions, we have 9 questions that we're going to be dealing with. And then from those 9 questions, we must leave spaces in between. Okay. And then give brief motivation, discussions, an appropriate mathematical formula can be used. Okay. A calculator that is reasonable and approved should be used. And yes, you're advised to detach the data pages. Okay. So question number 1. Okay, so we have four options that are provided, and we must choose the correct option. So the number of wave pulses per second will be known as the frequency. Okay. Okay, the number of complete waves that are passing a point in 1 second, that is known as the frequency. One point two, if we have 2 diagrams or 2 pulses shown below, okay, all of them are crests. So it's a 30 centimeter, it's a 10 centimeter. Okay, but the direction is opposite. So when these 2 pulses, the diagram meet at point X, what will be the type of interference that's going to happen? Okay, so since both of them are crests, then we're going to have a constructive interference. Okay, so then we have a 30 plus a 10, we end up with 40 centimeters. So C is the best option there. And then 1.3, a certain electromagnetic wave has this much of energy, and then they want us to get the frequency. So if we use the Planck's formula, H is equal to E is equal to H frequency, whereby the E is the 4,97 times 10 to the negative 14. And what's the Planck's constant? 6,63 times 10 to the negative 34 F. Then you divide by 6,63 times 10 to the negative 34 divided by 6,63 times 10 to the negative 34. Okay, so our frequency should be having a positive exponent. What is 34 minus 14? That's a 20. But then if I divide this, it's going to give me a 0, something, which means B is the best or the most reliable answer there. 1.4. In the following circuit, the bulbs are identical when the switches, or which switches must be closed for A only to light up. Okay, so if you close this switch and leave this open, it's only B that's gonna, but even B will not light up because you have to close 3 and 1 for B to light up. So for A only to light up, you need to close S2 as well as S1. Okay, so S1 and S2, which is option B. And then a straight line difference in the position in space is called a straight line difference. Okay, in position in space is called, that is known as the displacement. No? Then if you consider the vector diagram below, okay, we have vector A, we have B, we have C. Which of the following correctly describes the relationship between A, B, and C? So if you get A, you minus B, you'll get C. That's what I'm seeing. It's A minus B should give us C. Arrow. or the other way around? Is that true? Is that true? Oh, someone can say that if you get A plus a B, okay, this is a plus B. That's what we're saying. A plus B, C, so option A is the best. And then 1.4, the kinetic energy of a moving body will increase the most if velocity is doubled, the mass is doubled, velocity is halved, the mass is halved. I think option A is the best, okay? Because we know that the EK is a half mv squared. So if the velocity is increased, definitely the energy will also increase. All right, then question number 2. Question number 2, diagram below represents a transverse wave produced by a source, okay? We're seeing the distance d and then the time, okay? And then they want us to define what the transverse wave is. So we know that a transverse wave is a type, okay, whereby the particles, okay, in the medium, it's a type of wave in which the particles in the medium will vibrate perpendicularly, or we can say at right angles to the direction of propagation, to the direction of motion or direction of propagation. And then 2.2, they want us to write down the amplitude in meters of this wave. So we know that the amplitude is just the maximum displacement. So if this is our zero line, the highest point reached is 40 centimeters, should be changed to meters. So it's going to be 40 divided by 100, which becomes a 0.4 meters. And then they want us to get the period of the wave. So period is basically the amount of time that it takes to get one full wave, okay? So the question is, if we are starting from here as our reference point, and then the full wave is just going to complete at this point. So from 0 up to 8. So meaning that we have 8 seconds. That becomes the period. Alternatively, someone can look at the crest and the trough, and yeah, you'll get there. Because if this is a 2, this is going to be a 10. So 1 trough, 1 crest. 10 minus 2, still 8. Okay, and then if the distance d is a 0.9 meters, okay, what is the name of the physical quantity given to distance d? Okay, so what we call the distance that one full wave covers, that is known as the wavelength. Okay, then 2.4.2, calculate the speed of the complete wave that is shown in the diagram above. What do they need? They want the speed. Now we know that V is given as F what? F lambda, okay? The only thing that we need to find is just the frequency because we already have the wavelength. Do we have the wavelength? Yes, we can get it, or we have it already. Okay, so we know that frequency is given as 1 over the period, and then 1 over the 8, we're going to get 0.125 hertz. Then let's substitute that side. So V is going to be our frequency, which is 1025. And then the wavelength, we saw the distance, they told us it is 0.9. So 0.9. So this ends up with a 0.11 meters per second. Okay, so that is 2.4. Then 2.5, the following sound wave produced by a turning fork is observed by an oscilloscope. Okay. And then the question is, a few more notes are played on different turning forks and the patterns are observed. Identify the wave as transverse or longitudinal. So this is going to be longitudinal. Okay, because this sound longitudinal. And then which one of the above patterns A, B, C represents a louder note than the original? So if this is the original is 1, 2, 3 blocks. This is 2 blocks only. 1, 2, 3, 4. Okay. This is 1, 2, 3. So this one is the same. This is smaller, and then it should be not B. The reason being, the amplitude is greater. Okay, so 1, we are saying it has a greater amplitude. It has a higher amplitude. That is also one other option. Then 2.5.3, above which frequency is a sound wave classified as ultrasound? Now, for as long as the frequency goes above 20 kilohertz, okay, or 20,000 hertz, then we know that that sound should be classified as ultrasound. The name one use of the ultrasound in the medical treatment of patients. Number one, we use them to determine, used to determine the rate of blood flow. The rate of blood flow, that's one. Two, we can use them for monitoring the fetus. Okay. And then next, we can also use them for diagnosing what we call the tumors for cancer patients. Okay. So basically those are three, but we can use just one. Okay. The other one can also be used to clean the medical equipment and so on. Question number 3. Electromagnetic spectrum includes, amongst others, we have the radio waves, the ultraviolet, gamma rays, visible light, X-rays. How are electromagnetic waves generated? So if we have what we call the accelerating charges, okay, accelerating charges, when charges are moving at very high speeds, then we create what we call the electromagnetic waves. And then explain what is meant by the dual nature of the electromagnetic radiation. Okay, so this can be explained. Okay, we use what we call the wave model. Okay, we wave model, and then we also have what we call the particle model. So if we can use the wave model and the particle model, then we can be in position to explain what the electromagnetic radiation is, because when you use the wave model, it brings it out properly. And then if you also use the particle model, it also describes most of the properties of the electromagnetic radiation. And then 3.3. Okay, from the above, name the electromagnetic radiation that is used in hospital to identify broken bones. So those are basically the X-rays. And then which one is used in Wi-Fi or wireless fidelity? So those are radio waves. Okay, and then which one has the highest frequency? So the highest from what we were given is basically, not the highest energy, not frequency, is basically the gamma rays. All right, then 3.4, calculate the energy of a photon of microwaves with a wavelength of this much. So Planck's formula or Planck's equation E is equal to HF. It's going to be 6,63 times 10 to the negative 34 multiplied by the frequency 2,1 times 10 to the negative 2. When I punch this into my calculator, does this make sense? Wait a minute, they gave me the wavelength and not the frequency. Okay, so meaning that I have to change this around. Okay, so if we have the wavelength, we know that V is equal to F lambda. Okay, our problem is the F, so we're going to replace F with a V over lambda. Okay, so what I'm going to do, I know that the V represents the speed of light, okay, which is 3 times 10 to the 8. Now I'm dividing it by my wavelength, which is 2,1 times 10 to the negative 2. Okay, so when I punch this into the calculator, I'm ending up with 9,47 times 10 to the negative 24 joules. All right, then question number 4. Diagram below shows two small identical spheres D and E on an insulated stand. The spheres are brought together to touch and then they are separated after touching. And then the sphere or the charge on sphere D and E is basically a positive 5 nanocoulomb. 4.1. If the charge on D was before the sphere is touched. Calculate the initial charge on E. Okay, so one thing we need to know is that for us to get the charge, we must get the charge initially or the charge before plus the charge after divided by 2. So if our final charge is a 5 times 10, should I use the nano or let me just leave it as a 5 nanocoulomb. And then the charge before is what I'm looking for. The charge after, wait a minute. Because we have a negative 2 here divided by 2. When I cross multiply, I have 10 nanocoulomb is equal to negative 2 nanocoulomb plus the charge before. Let's move that aside, meaning that we're going to have 12 nanocoulomb as the charge that was on E. So it's B and then E, and then we get that. Okay. It's a D. Okay. Then 4.2, calculate the number of electrons that were transferred. So we need to get the difference between the charges. Okay. So in that case, if I have a 5 nanocoulomb minus negative 2 nanocoulomb, this gives me positive 7 nanocoulomb. So this is the amount of charge that was transferred. But I know that N is given as Q over E. So my charge is 7 times 10 to the negative 9 coulombs. The electron charge is basically 1,6 times 10 to the negative 19. So when I punch this into the calculator, I'm ending up with a 4,37 times 10 to the exponent of 10 electrons. And then 4.3, were electrons transferred from D to E or E to D? So if originally the charge on E is a 12 nanocoulomb, the charge on D is a negative 2 nanocoulomb, we can see that the E is more positive, D is more negative. So electrons will always flow from a more negative section to a less. So it has to be D to E. Okay, so that is question 4. And then question 5, the circuit diagram below shows 3 resistors connected to a battery. The voltmeter that is over the 4 ohm resistor is reading 12 volts. And then V1 and the ammeter connected as shown in the diagram below. The resistance of the battery can be ignored. Okay, they want us to define what potential difference is. So potential difference is basically the energy transferred. Okay, is the energy that is transferred per unit electric charge. Per unit electric charge that is flowing through it. And then they want us to get the total resistance. So 5.2. What we can see with the total resistance is that these two are in parallel. So we're going to say the product over the sum, which is 2 times 2 over 2 plus 2. It's a 4 over 4, which is a 1. Okay. And then that 1 is going to be in series with the 4. So I'll say 1 plus the 4, which gives me 5 ohms. Okay, so that is how we get the effective resistance there. And then 5.2.2, they want us to get the amount of charge that is flowing in A1. Okay, this is A1. So in other words, we need to get the total current if the time is 120 seconds. Okay, so since we have the resistance, we know that V is equal to IR. Okay, they gave us the voltage to be 12. Not so. But do we even have to go that side? Let's start by writing the formula of charge, but what were we told? We don't need to calculate that. We know that charge is IT. Okay. We were given 1.5 amps, 1.5 amps. When we add these two, we get the 3 amps that are flowing through this A1. I mean, that's going to be a 3 multiplied by 120, which is a 360 coulombs. All right, and then 5.2.3. They are telling us that reading V1 of the voltmeter uses 5.4 joules, okay, of energy, and the same amount of current calculated in 5.2.2 flows through it. So if this is our energy, and then we're saying the current is also 3 amps, what does the question want? Calculate the reading on V1. Okay. So in other words, we need the voltmeter reading. Voltmeter reading if we are given this. So this would represent more like the power. Okay, because power is more like the energy or the work done. So what we can use is a formula that has work done. We know that work done is given as the same as V multiplied by Q. Okay, we can use this. But what do we know? We know that our V is going to be W over Q. That's just because I don't want to use the VIT because we don't know the time. So the work done is 5.4 over the 360, meaning that the voltmeter reading there is going to be 14 volts. Okay. And then 5.3, a wire with negligent resistance is now connected from X to Y, meaning that instead of us having all of this, you can just have one simple wire that is connected there. Okay. How would the reading of V1 be affected? So where is the position of V1? You can see that V1 is the main voltmeter. Okay. So how is that gonna be affected? Is it going to increase, decrease, or stay the same? So the voltmeter reading is going to decrease. They want us to explain. Okay. Now, what we can see is that connecting a wire simply takes off all these two resistors. Okay. Meaning that this one is taken away. Okay. So we're going to say that connecting the wire, it decreases the resistance, to just 4 ohms. Okay. And it will also make it to be in series. Okay. And if that is the case, simply means that the total resistance will reduce or will decrease. And if resistance decreases, the current will increase. The current will increase, and then the potential difference will decrease. Potential difference will decrease. Okay, so that is how question 5 would have been approached. Question 6, they're telling us that in Paris 2024 Olympics, this lady won the gold medal, the 100-meter breaststroke event, when she completed the event in 65 seconds. The pools are 50 meters in length. Define what average speed is. So average speed is basically the rate of change of velocity. And then calculate the average speed. We know that the speed must be given as the distance over the time. So what do we know with our distance? Our distance or displacement is going to be 100 meters. The time is 65 seconds. So you're going to say 100 divided by 65 seconds. This gives us 1.54 meters per second. Okay, going question number 7. They're telling us that there is a taxi. Okay. And this taxi is traveling at a constant speed of 84 kilometers per hour in a straight line and level road where the speed limit is 60 kilometers per hour. Define acceleration. So this is the rate of change of velocity. Rate of change of velocity. Then they want us to convert 84 kilometers per hour to meters per second. So what we're going to do is we're just going to divide this by 3.6. Alternatively, change the 84 kilometers to meters. So it's 84 times 1,000 divided by hours to seconds is going to be 3.6. Okay. So when you sort this out with a calculator, you're getting a 23.33 meters per second. And then a traffic officer starts his car from rest, okay, which means VI 0. As the taxi passes him, the traffic officer accelerates uniformly at 2 meters per second up until it reaches the maximum of 25 meters per second. Calculate the time, okay, that it will take the traffic car to reach its maximum. Okay, so what we can do, we can use the V final is equal to V initial plus A delta T. What do we know? We have our V final, which is a 25. Our V initial is a 2. No. The V initial is a 0 because started from rest. The acceleration is 2. Okay. And then 2t is equal to 25 divided by 2, which is a 12.5 seconds. And then 7.4, determine by calculation which vehicle the text of the traffic car is ahead after t seconds has passed. Assume that the taxi maintains a constant speed. So what we're going to do in this case, we know that the distance that's going to be traveled is the same after a certain time t. So let's start by looking for the displacement, which is the distance traveled, V initial delta t plus a half A delta t squared. Okay. So our V initial for the taxi was 0. Or we can use the one for the traffic cop's car. That's a half. The acceleration, we can use 2 into 12.5 squared. Okay, when I simplify this, I end up with 156.25 meters. So this is the distance that needs to be traveled. Okay. Then with the taxi, if I do the same thing with the same formula, it's going to be a 23.33 multiplied by the same time. We want to see after that time, how far will the taxi be? So this is a half, since the speed is the same, okay, it's the constant, which means the acceleration is going to be a 0. Okay, so this whole thing dies out, and then I end up with 291.63 meters. So after 12.5 seconds, we're saying that the taxi will be ahead, will still be ahead after 12, that much. Okay. Question number 8. A driver stops his car at the red traffic light. The graph of the car's velocity against the time shows its motion for 8 seconds from the time the traffic light turns green. Okay, so there is our graph, and that's our information. Okay, they're telling us that the shortest or the short time interval between the traffic light turning green for go and the driver responding for the signal is known as the driver's reaction time. Okay. How long does the driver take to respond when the traffic light changes to green? So that is from 0 up to this point. That's like 0.8 seconds. And then 8.2, determine the maximum speed. So the maximum speed that the driver went, because this is going to be the highest speed. And it's more like halfway, because 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's 15. So it's a 2.5. So 12.5 should be more or less our answer. So that's 12.5 meters per second. And then use the graph only. No equations, calculate the average acceleration. So when you're looking for the average acceleration, you're technically looking for the gradient. Okay, so if I look at this as a 12.5, and I know that I think that's all I need. What's the reading here? It's going to be 5.8. So the change in velocity over the change in time means that I'll have a 12.5 minus 0 over 5.8 minus a 0.8. So 12.5 divided by 5. This gives me, what does this give me? Gives me a 2.5 meters per second. All right. And then use the graphs only again to determine the displacement. Okay, so when I'm looking for the displacement, I need to look for the area that is under the graph. Okay. Displacement needs to be the area that is under the graph. So let's see. If our height is 12.5, what is the distance there? Because this is a 5.8 and 8, which is going to be like a 3.2. 3.2, 5.8. I don't know. We can use that and see. So if I try to get the area of a trapezium, no, they say determine the displacement of the car over these 8 seconds. Which 8 seconds are they focusing on? Okay, so okay, I get it now. So I'll say a half h, a plus b, I can do this. So 1 over 2, our height is a 12.5 into the a is a 3.2 plus 5.8. If I punch this into my calculator, what do we get? Okay, 12.5 multiplied by 0.5 into 3.2 plus a 5. But is it a 5.8? It cannot be a 5.8 because now this is 8 and then this is a 0.8. There's a difference there. 8 minus 0.8 gives us a 7.2. Okay, so this needs to be a 7.2. Okay, 7.2, I'm getting 65. Okay, that is 65 meters. I don't know why I'm getting that, but do we need to subtract this? Because if this is 3.2, we are subtract because at this point it's like it's constant, it's not changing at all. Okay. If I look at 3.2 multiplied by 12.5, it is a 40. And it's not going to make sense. So that's how I would have obtained that. Alternatively, you can break it down, okay? And then you find the area of each section, okay? Find the area of each section. Maybe it's me that is having wrong values here. Because how is this? It's a 2.2 and not a 3.2. Let me just punch it back and see what I get. We say 0.5 times 12.5 into 2.2 plus a 7.2. It's not that, it's a 58.75 meters. Okay, so that is question 8. Then question 9. Now telling us that the graph below shows energy against the position of the pendulum bob, that is 50 grams, as it moves from A to B to C to D. Okay, define what gravitational potential energy is. Okay, so we know that is the energy that the object will have based on the position or based on its position. So the energy an object has due to its position. So the position must be within the gravitational field, which is like the Earth or the universe. 9.2, determine the maximum potential energy of the bulb. So you can see that the highest point that it's going to is somewhere halfway in between. So we're going to call it 0.3. Okay, that's 0.3 joules. And then calculate the maximum gain in height of the bulb. So we need to use the formula and say that EP is equal to mgh. Now we have the energy as a 0.3. The mass is 50, change it to kilograms, it's going to be 0.05 multiplied by 9.8 h, meaning that the h is going to be a 0.3 divided by 0.05 multiplied by 9.8. Okay, so what does this give us? What does this give me? I'm getting a 0.61 meters. Okay, and then calculate the maximum speed. Now from the conservation of energy, we know that the mechanical energy at maximum or mechanical energy is conserved. So let's say the EP max should be the same as the EK max. So if we got our maximum kinetic energy to be 0.3, it should be equivalent to a half mv squared. Okay, it's a half mv squared. Then 0.3 should be a half the mass. You got 0.05 multiplied by v squared. And then if you do your magic, move everything to that side, it's going to be the square root of 0.3 times 2 over 0.05. And this gives me a 3.46 meters per second. All right, then 9.5. They want us to state the law of conservation of mechanical energy in words. So what this tells us is that the total energy, okay, so total energy in an isolated system, remains constant. Total energy in an isolated system remains constant. So guys, this brings us to the end of this paper. I wish you guys all the best in your preparations. Let's meet when we are discussing paper 2. Bye-bye.